Hi, my name is Natasha binti Mama SAUPI and my matric number is D202010955542. Okay, so let's start with the endpoint extrema definitions. Okay, the definition is an extremum of a function that occurs at an endpoint of the domain is given a separate in the easiest way. Okay, endpoint extrema has high point and low points of a functions. For example, Ts is defined on closed interval containing B if dB is less than or equal to the Gx for all x interval. dB is a minimum. If dB is more than or equal to Gx for all x in interval, dB is maximum. Okay, I want you to get an idea here. I just want you to get an idea here. This is a graph. You just need to put on a graph just 0 until 8 for fx and 1 until 6 for x. So let's say that I plot close interval between x equal to 1 and x equal to 5. Is it continuous on the closed interval or is not? What do you think? Yes, it is continuous on the closed interval. What about if I put here g of 1? It will be a minimum. Why? Because g of 1 would be the lowest value for this function, while for g of 5f is the maximum because it has the highest value for this function. In this topic, we have theorem 3. If the function f has an extremum at C, then either C is an endpoint of the domain of f or C is a critical point of f. For example, we can find the extrema of the following function, which is fx equal to 1 over x squared plus 1. By following the rule, then 1 is u, x squared plus 1 is v. So we just plug in into the formula dy dx equal to v times u prime minus u times v prime over v squared. So you need to remember which one is u and which one is v, because we have to plug in into the equation. So as for me, I will rewrite the value for u and u prime same goes to v and v prime because it will be easier for me to plug in to the equation. Okay, so you just need to start dy over dx equal to x squared plus 1 times 0 minus 1 times 2x, and we divided it by x squared plus 1 squared. And I have a question for you guys. Where is rule that being used here? So you just need to comment in the section comment below. Okay, and I will take it as you give me an answer. So we will get the answer, which is negative 2x over x squared plus 1 squared. The derivative of fs equal to 1 over x squared plus 1 is f prime s equal to negative 2s over x squared plus 1 squared, which is defined for all s and is 0 only for s equal to 0. Thus, 0 is the only critical point of f. Also, there are no endpoints of the domain of f. So, the only place an extremum can occur is at s equal to 0, since f0 is equal to 1 and fs is less than 1. If s not equal to 0, f has an absolute maximum at 0. Okay, so let's proceed to the first derivative test for local relative extreme values, which is it has theorem 4. Okay, so we got an example here, which is fx equal to 1 minus x power of 4. So the derivative of the fx equal to 1 negative minus x power of 4 is f prime s equal to negative 4x power of 3. How can I get 3 power of 3? You must subtract it with 1, 4 minus 1, and take it 4 in front of the x, which is 0 only at x equal to 0, since f prime s is greater than 0 for x less than 0 and f prime s is less than 0 for x greater than 0. F has a maximum at 0. This maximum is absolute. In this video, we are going to use the second derivative test to determine if there is any relative extrema in the function, if there is a relative maximum or a relative minimum. So let's talk about relative maximum or a local maximum. In order to get a local maximum, the critical number has to be found, so the first derivative has to be equal to 0 at some point C. So C is the point where the local maximum will be located along the x-axis. So f prime c has to be equal to 0, and the second derivative c has to be negative or less than 0. Whenever the second derivative is negative at a critical number, is going to be concave down. So as you can see, it will be concave down. So you could have this shape, and you see clearly from the graph that there is a maximum point, and that's going to be the c value that we need. That's where we have the horizontal tangent, which is typical of a local maximum or a relative maximum. Now, to use the second derivative test to identify the local minimum which will occur at a critical number, f prime c must be 0, so that's how we could find the critical number. And the second derivative at the critical number has to be greater than 0 or has to be positive, which means that it has to be concave out. So we were going to have the shapes, and we can see that we have a minimum at the bottom. Let's work on an example problem. Let's say that f of x is 2x cubed minus 12x squared. So let's determine the first derivative so we can identify any critical numbers. The derivative of x cubed is 3x squared times 2. Well, let's do it one step at a time. The derivative of x squared is 2x. So 2 times 3 is 6. 12 times 2 is 24. Now, to find the critical numbers, we need to set the first derivative equal to 0. Now, let's factor out the GCL, which in this example is going to be 6x. So 6x squared divided by 6x is negative. 24x divided by 6x is negative 4, and you will get this. Then 6x divided by 6. We can see that the first critical number is at x equal to 0, and we set x minus 4 equal to 0 and then add 4 to both sides. The second critical number is x equal to 4, so I'm going to write that at the top over here. So we have two critical numbers. Now let's find the second derivative to determine the concavity. So we said that the first derivative was 6x squared minus 24x. Now for the second derivative, it's going to be 6 times the derivative of x squared, which is 2x, and 24 times the derivative of x, which is 1. So that's going to be 12x minus 24. Now let's see the second derivative equal to 0. Let's take out a GCF, which is 12, so we have a potential inflection point at x equal to 2, so let's create a sign chart. If we plug in a test point greater than 2, let's say 3 and 2, at the second derivative, 3 minus 2 is positive. If we plug in a number less than 2, let's say 1, 1 minus 2 is negative, so it's concave down between negative infinity and 2, and concave up between 2 and infinity. So therefore, the second derivative test at 0 we could say is less than 0, because 0 is between negative infinity and 2. Now granted, you could just take this number and plug it into this expression. You really don't need to create a sign chart, you just keep that in mind. So for the second derivative, instead of using a sign chart, I evaluate f double prime of 4, so that's going to be 12 times 4 minus 24. 12 times 4 is 48, 48 minus 24, so that's positive, and as you can see, 4 is between 2 and infinity, so that's going to be positive as well. So f double prime 4 is going to be greater than 0. When the second derivative is less than 0, it's going to have a negative sign. And when it's greater than 0, that means it is positive. When second derivative is positive, we have a graph that concave up, and when the second derivative is negative, it's concave down. So you can see that a concave up graph is associated with a minimum, and a concave down a graph is associated with a maximum. So at x equals 0, we have a maximum, and x equal to 4, we have a minimum. So that's how you can use second derivative test to determine the relative extrema in the function. You need to find critical numbers and then find out what the second derivative is at those critical numbers. And now let's confirm our answer using the first derivative test. So let's put the critical numbers on this number line now. We need to rewrite the first derivative on its factored form. So it was 6x squared minus 24x, and if we take out 6x, it's going to be 6x times x minus 4. Let's see if we plug in a test point that is greater than 4, like 5. 6 times 5 is positive, 5 minus 4 is positive. If you multiply two positive numbers, that will give you a positive result. Now let's plug in a number between 0 and 4. Let's try 2. 6 times 2 is positive 2. 4 is negative, a positive and negative equals a negative. Now if we plug a negative 1, 6 times negative 1 is negative. A negative times a negative is positive number, so going to negative, the function is increasing and then it's decreasing. So this indicates that we have a maximum at which indeed we do, and going from negative to positive is to decrease and then increase. So that is a minimum at 4, which we do have, and that's you can use That means that you can use the first derivative test to confirm the result.